Hello. So this video is intended to substitute a class session that I'll be missing on Wednesday, October 16th. For me, in real time, it is October 12th, at least according to my computer. The reason why I'm doing this is, as I've previously mentioned, I have to be down in Southern California. But I wanted to do these videos so that you didn't miss out on some important material that we'll be learning about. Today I want to talk about implicit differentiation and logarithmic differentiation. I want to go through those a little bit quickly and then maybe say something about related rates to prepare us for a robust discussion of that in the next video. Let's get back to where we were. Just a real brief review of what we did. Yeah, implicit differentiation here. Sorry, yeah. So what we've been doing up until this point is what one might say, what one might call explicit differentiation. This is where you have an explicit functional relationship between two quantities x and y. The example that I brought up last time was of putting a kettle with water on a stove and as a function of time, viewing the temperature. So maybe in this case, x is time, and maybe y is temperature, and there is some kind of functional relationship between y and x. And people like Newton and other people concerned with the sort of early mathematical aspects of modeling the physical world were interested in these kinds of relationships, and interested, of course, in how these relationships changed as time changed, right? In which case you would be interested in the derivative dy dx of the temperature with respect to time. And when you establish a relationship like this, it's easy to compute what dy dx is. It's simply the derivative f prime of x. So that if f of x was something like sine of x, then f prime of x would simply be the derivative of sine of x, which, as you know, is cosine of x. But the point is that there can be more complicated relationships. There's nothing that nature doesn't require the relationship between two quantities to be given by something like y equals f of x. It could be more complicated. For example, you could have a relationship like this: x squared plus y squared equals 1. This is more complicated because this is not a functional relationship. If you tried to solve for y in terms of x, it's not that you couldn't. You could. Here's the solution. These are the set of all y's which satisfy this equation here for fixed value of x. But that you can't express y as a function of x. And that, but I don't think I said this out loud, and maybe that was an oversight. Notice that that's because when you draw the set of points x comma y satisfying this equation here, you get a circle, and a circle manifestly does not satisfy the vertical line test. So this is not the graph of a function, is the bottom line. Okay, so if we want to be able to say something about the way in which y changes, dy dx, we have to do something slightly different. Sorry, I said we have to. We don't have to. I'm sorry. We could take essentially two derivatives. One derivative for the positive branch of the square root here and one for the negative branch of the square root here. We would get two different answers depending on which side of the circle we wanted to be sort of working with. And it's not that there's anything wrong with that. Nothing wrong with that. You can do that. You can proceed in that way. But is there another way where which might be applicable in situations where it's much more difficult to solve for y? Here, this was relatively easy to solve for y. Other situations that we might have might be very difficult to solve for y. So is there a way of getting at dy dx in those situations? The answer is yes, and the method is called implicit differentiation. Here we did implicit differentiation. The key move in implicit differentiation is in going from terms like this to expressions like that, which become expressions like that. That's really the spirit of implicit differentiation. Let me explain the thinking. If you're taking the derivative of y squared with respect to x, the idea is that you first take the derivative with respect to y. That's what's written here. That's what's written here in green. You first take dy of y squared and then multiply the result by dy dx. Now, that's a lot of letters to write down in a row, and you might be asking yourself, how did they come up with that? How did you do that? You referring to me. How I did it is to think about this dy down here and the dy up there kind of canceling one another. You see, so the dy's kill each other, and then you're kind of left with like d over dx times y squared. I mean, it's all very flaky, okay? It's not quite right, but it works as a sort of mnemonic, okay? And the reason that it works is because of the chain rule. This is what the chain rule tells you, yeah? It's the reason that it works. And it's the reason why when people tell you, don't do that, they're not, dy dx is not a fraction. I mean, they have a point, okay? But the chain rule is what makes that sort of go. And there's other reasons why, where it sort of works in the right way. There's other points of consistency with other existing bodies of mathematics. But we don't need to get into all that. Suffice to say, it works here, so let's use it. Dy of y squared is 2y times dy dx, and then you can solve for dy dx algebraically, and you get this result here. We went through a problem involving a tangent line, and we talked about finding the equation of the tangent line to this curve here. Now, I just want you to appreciate, if you were to try to solve for y here, you would kind of have a bad time trying to solve for y in this expression. I'm not going to say that it's impossible, okay? But it's just going to be somewhat tedious and gross. Better, if you want dy dx, to approach it using implicit differentiation. And this is the result that we got. Please scrutinize this solution if it seems mysterious. Really, it's just the chain rule again. And yeah. Okay, well, I want to finish this problem because I didn't actually find the equation of the tangent line yet. We're going to use this dy dx that we've computed here to finding the equation of the tangent line. Let me just get a new sheet of paper and record this information. So dy dx we found was 2x minus y squared divided by 2xy plus 2. Okay, great. And now what that allows us to do is figure out the slope of the tangent line in question. The slope of the tangent line in question is dy dx evaluated at the point 1, 1. Now, where 1, 1, that's just given to us, okay? So just chill out, all right? That's given to us. So we're going to plug 1, 1 in to dy dx. What do I mean by that precisely? I mean that in place of x, I'm going to replace 1, and in place of y, I'm going to put in 1. So what I get is 2 times 1 minus 1 squared divided by 2 times 1 plus 2. And now this is arithmetic, right? And what this ends up being is 2 minus 1 divided by 2 plus 2, which is 1/4. So voila, we've got the slope of the tangent line now. All right. We also know a point which lies on this line. That's given to us. That's 1, 1. So in principle, we know everything. Because we know that for any line in the plane, any line in the plane is given by two pieces of information. If you specify two different pieces of information about a line in the plane, then you will determine that line. And that comes from the old sort of idea that in y equals mx plus b, there's sort of two knobs that you get to turn, m and b. And if you know m and b, and if you don't know m and b, but you know two additional equations, okay, two additional what we call constraints, then you take the 2 degrees of freedom represented by m and b, you cut them down by 1, and you're left with 0 degrees of freedom. And what does it mean? What does it mean to have 0 degrees of freedom? It means that there's oftentimes a unique solution or a discrete set of solutions. Okay, so anyway, let's use that idea here. We start with the form for a line y equals mx plus b. We incorporate this information about slope to obtain the fact that y must be therefore 1/4 x plus b. And then we incorporate this information about the point to obtain the equation that 1 is equal to 1/4 times 1 plus b. How did that happen? Well, because this point 1 comma 1 lies on the tangent line, it has to satisfy this equation. So when I plug in 1 and for x and 1 for y, because of the fact that the coordinates of this point are 1 comma 1, I get an equation like this, which should be true. But because this is true, I can now figure out what b is through arithmetic, because I subtract 1/4 from both sides, so I learned that b is equal to 3/4, which tells me that the line is given by the equation y equals 1/4. What am I doing? Why did I do that? Why did I do that? 1/4 x plus 3/4. That's my y equals mx plus b thing. Just ignore that. It didn't happen, okay? All right. Let me show you in Desmos what this curve and together with this line look like. So here's Desmos. Let me first put in the equation of the curve. That is xy squared minus x squared plus 2y y equals 0. Really? That's what it looks like? Did I do that right? No, I didn't want 0, right? We wanted 2. I apologize. That's what it looks like for 0. Here's what it looks like for 2. Okay. I'm going to set this thing equal to 2. Okay, and you'll probably observe right here, look at that point that my mouse is pointing at. You see that that point there has coordinates 1 comma 1, right? And indeed, 1 comma 1 lives on this green curve. Why? Because when you plug in x equal to 1 and y equal to 1, the equation is satisfied, right? Okay. Now let's plot the line in question. The line that we came up with for the equation for the tangent line that we came up with was y equals 1/4 x plus 3/4. Yeah, there we go. And look at that. That's the purple. The purple line is the tangent line. The green thing is the curvy curve, okay? And you can see how at 1 comma 1 is perfectly tangent. Now, what is the value of knowing this? Okay, great question. Let's zoom in on 1, 1. You can see right now the green curve and the purple line are different, right? But as we zoom in closer and closer on 1, 1, you can see that the green thing is getting closer in some sense to the purple thing. And that if we zoom in a lot, well, now there's just a tiny difference between green and purple, but if we zoom in a lot, that difference will more or less vanish. To the point where now we can't even see the green curve because it is so well approximated by the purple line, okay? So in particular, as we zoom in like this, we can see the sort of instantaneous rate of change in the values of y as we change x are going to be well approximated by the rate of change in the purple line as we change x. But we understand rates of change when it comes in the values of y when we change x, because that's what the slope of the line tells us, right? In this case, the slope of the line is 1/4. And so what that's telling us is that it is equally true that the rate of change, if you like, of the purple line at the point x equal to 1 is 1/4. It's equally true to say that that's also the rate of change of the green curve at x equal to 1. So that if the green curve were useful in measuring, let's say, the relationship between time and temperature of some kind of physical system or whatever, that we could say that when x was 1, or what if x represented time, if time is 1 second, then the temperature would be increasing by at a rate of 1/4 degrees Kelvin or Celsius or whatever, Fahrenheit, whatever, per second. Hopefully that makes sense. Okay? Alrighty. Let's do one more problem, shall we? Just one more problem. And I want to do a problem from the worksheet that I gave to you. So let me pull up that worksheet. Here? Yeah. So this was the worksheet that I gave you about implicit differentiation. This is on the Canvas shell. And I want us to try to attack and kill exercise 12.2. Remember the mechanics. The mechanics are the chain rule. That's the underlying principle which allows us to take things like the derivative of something like y squared or the derivative of natural log of y. If you need a reminder of what that looks like, please rewind this video when I was talking about that, or take a look at the solution from that we did in the last video, and take a look. But I really want you to try, okay? So I want you to, I don't know what you're doing right now, okay? Don't know. I can't see you, and make fun of you if you aren't paying attention. But if you are diddling your phone, diddling something else, or maybe you are just sort of completely spaced out, what I want you to do is put all of that distraction aside, okay? Get a piece of paper and try to do this problem at exercise 12.2 here. I give you the answer, but of course the answer is useless without a process by which we can arrive at that answer. So I want you to try to write out or figure out what that process is, okay? And please try, okay? Because as I've said already, and I don't mean to give you yet another pep talk in this direction, it's important that you actually try and test yourself to see where your understanding of this material might be lacking, or where there are confusions or whatever, so that we can fix those things together, okay? We can only begin to solve a problem when we have identified that problem. And I don't want you to have to solve that problem on, say, a midterm or a quiz, final exam or whatever, a quiz. I want you to solve that problem in low-stakes situations such as this one here. But it does mean you have to try. Okay, so please pause the video, give this your best shot, and let's come back. Okay, did you try? I hope so. And let's take a look at what the right process, or at least the process as far as I'm concerned, should be to kill this problem. Yeah. And listen, I don't mean to, I'm not trying to be patronizing or condescending. I'm really not. There's just a well-tested formula for being successful in college. And I know that every one of you wants to be successful at the college level. It's just that sometimes, not always, but sometimes your high school education and your elementary school, to get your K through 12 education does not prepare you for the rigors that are expected when you're at the college level. And so I'm trying to make very clear to you what those rigors are, what it is that we expect you to be able to do when you're in a university level math course. And please understand that the expectations that I'm setting forth are not weird, okay? Every single one of your college instructors is going to expect the same, maybe even more. So it's time to level up. It's time to sort of develop a work ethic around trying instead of just passively consuming. And I'm not saying that you're necessarily doing that, but I am exhorting you that if you aren't, please do, okay? Because I want you to be successful. All right, enough of that. Let's do this problem. So we want to find dy dx. This is exercise 12.2. We want to find dy dx. Can you read that? Yeah. Find dy dx, where we have the following relationship. X squared plus y squared is equal to the natural log of y plus e to the x. Cool. So the first step, because we want to sort of get dy dx out from this information, you think of this as like a rock, and we're trying to mine out the gold of dy dx from it. The first step is going to be to ddx both sides of this equation. And if we do that, we get ddx of x squared plus y squared is equal to ddx of natural log of y plus e to the x. I guess I could do this, right? And then we're going to use the sum rule. So the derivative of a sum is the sum of derivatives. So we get d dx of x squared plus d dx of y squared is equal to d dx of natural log of y plus d dx of e to the x. There are bits which are easy and bits which are a little bit more complicated. The bits which are easy are this and that. The two that my index fingers are pointing at. This one is just 2x. And that one is just e to the x. I'll get to that. But for this one right here, we have to be a little bit careful. Now, the wrong answer is 2y. If you just wrote 2y, that would be incorrect. Because what you would have really been doing there is taking the derivative of y squared, and this is important, with respect to y. Okay? Not with respect to x, which is what is being instructed, or which is what this thing here is communicating. We want to take the derivative of y squared as x changes. Okay? So how? Here's how. Chain rule is how. You are going to first take the derivative with respect to y. So d dy of y squared. That is 2y. But then you adjust your answer by dy dx. And that's good. That's the chain rule right there. Similarly here, with natural log of y, you're going to first take the derivative with respect to y of log y, and then multiply by dy dx. So we have d dy of log y times dy dx. Yeah? Now, don't be freaked out. Excuse me. Don't be freaked out by the fact that we have these dy dx's sitting here. That's what we're hunting for. That's what the problem is asking us to find. So it's actually a good sign that we have dy dx's sitting in here. Okay? And then we have d dx of e to the x. Great. Now we're in a position to figure out all of this stuff here. We have 2x plus 2y dy dx, right? That's d dy of y squared is 2y. d dy of log y. I slipped in. Yeah. As I've said before, mathematicians, when they write log, they mean the natural log. I know that isn't true in other contexts, but I've accidentally fell back into that. So what I meant to write here is natural log of y, or maybe what I meant to write is log y, but I'm just I am giving in to wider social expectations, for which the log of y is oftentimes log base 10 of y. Why it would be log base 10 and not log base e, as it is for natural log, I guess has to do with the fact that we have 10 fingers, naturally speaking, anyway. But that just seems like a limitation instead of any good principled reason. So, but whatever. Who cares? Dy dx. Yes? d dy of log y is 1 over y times dy dx. Dy dx is just that. And then do we have the e to the x there? Okay. Now, this equation, okay, we can then solve for dy dx with. How? We can get all the stuff involving dy dx on one side of the equal sign and all the stuff that doesn't involve dy dx on the other. Why? Because we are preparing to factor out the dy dx, and then that will allow us to isolate what dy dx is in terms of x and y only. Okay, so I'm going to move this term over to this side, and I'm going to move that term over to that side. Now, listen, this algebra stuff, okay, it's not optional. You got to know it, okay? So please, if what I said to you doesn't make sense, if it's not resonating inside of your brain, just go back, listen to it again. What I said was completely correct, completely on point, and a really good thing for you to understand. Let's segregate the terms involving dy dx from the ones that don't, and make the wall separating them be this equal sign. So I'm going to subtract. Here's just me doing that. Minus dy dx. Oh, no, I'm sorry, 1 over y. Dy dx, there's a minus sign there. Okay, equals, so I get e to the x minus 2x. I hope I did that right. Good. Yes, I did. Now I can factor out, again, I'm using the strategy here. I'm going to factor out the dy dx. Leaving the other side alone. And then I'm going to divide both sides by 2y minus 1 over y. Now, I don't know if you share my aesthetic sensibility. That's okay. But this looks kind of gross to me. And if there was a way for me to... Oh, and what's gross looking about it? It's the fact that there is a fraction inside of the fraction. If there's a way for me to fix that, I think I would like to take that. Because, yeah, there's... I don't know. Just doesn't look good to me. So, how? One way, of course, would be to clear out the denominator, so to speak, in the denominator. That is, multiply the denominator down here by y. Now, you know you can't just multiply like a denominator by y and not expect to compensate in some way. So you would multiply the top by y. Therefore, in essence, multiplying this fraction by a fancy version of 1, namely y over y, right? But you should be concerned, right? Because I was harping a lot this semester on being careful, on thinking carefully about things. And when we look at an expression like y over y, and we are being told that this is equal to 1, we should be suspicious. Because y over y is not always equal to 1. Y over y is only 1 if y is non-zero. If y is 0, we get 0 over 0 on the left here. And 0 over 0 doesn't exist. There's no such thing, at least in terms of a number equal to 0 over 0. Okay, so what do we do? Sorry, are we allowed? Is this okay? Maybe we should just leave our answer like this in light of that. Yeah, you could. There's nothing wrong with this. It's right. It just looks gross. But I claim, and I'm right, that we can multiply by y over y in this case. Why? WHY. Why? Not why. Why? Why? It's because y can't be 0. Look up here. Look. We have the natural log of y there. So implicitly, we didn't explicitly say it. We didn't explicitly write it down with our pen. But y can't be 0. That's already restricted by the fact that we have the natural log of y sitting here. Why? WHY? Because the natural log of 0 doesn't exist. The natural log of any negative number, the natural log of 0, does not exist. That's because the exponential function is always positive. And the natural log, being the inverse of the exponential function, only will accept positive values as input. I hope that made sense. So what I'm getting at is this issue is not an issue here. Y is not allowed to be 0 already. So we can multiply top and bottom by y and obtain a nicer looking answer of y e to the x minus 2xy, that's me multiplying the numerator by y, divided by 2y squared minus 1. And there's a good answer. Okay. I was about to ask if there are any questions about this, but I just realized you can't go back in time and communicate those questions to me. Furthermore, we are geographically separated. So we are separated both in time and space. So how are you going to communicate your questions to me at this time? You can't. Okay. I want to talk about logarithmic differentiation now, I guess. Sure. Here's a problem. And this is an example you can follow along with from the worksheet. So Oh, I only have 20 minutes. Okay, that's okay. Logarithmic differentiation. Okay, here is a function. Find dy dx where, and this is really an example, again, in the worksheet. Y is going to be given by 2x plus 3 cubed times sine to the 6th power of x divided by tangent of 2x. Now you're probably puking a little bit, and for good reason. Just consider, please, what would be required to attack and kill this problem using the techniques that you've learned thus far. If you didn't know anything else, and you just applied quotient rule, sum rule, product rule, chain rule, all of those things, you could in principle do this. I'm not saying that you can't. In fact, some of you would probably do this well, yeah, without issue. It would just be tedious. Logarithmic differentiation takes advantage of properties of logarithms that you learned about in high school, maybe, to simplify this expression before taking the derivative. What are those facts about logs that I want you to know about? So I just want to remind you of 3 properties of logarithms that are really useful here. And we'll use the good old natural log as our example of a log. Log of a product. If you have the log of A times B, you know what you're allowed to do? You can write that as the sum of logs. Yeah, so like imagine that you were talking about log base 10. Log base 10 of 100 is the same thing as log base 10 of 10 times 10, but that's the log base 10 of 10, which is 1, plus the log base 10 of 10, which is also 1, and 1 plus 1 is 2, and you know that 2 is the log base 10 of 100. Why? Because 10 squared is 100. Okay, so there's that. There's also a similar fact, but about quotients. Is that it's the difference of logs. Log of what's up top minus the log of what's downstairs. And finally, there's a way of dealing with powers. A to the c, which is equal to c times log a. Those 3 properties of logarithms will allow us, if we were taking the log of an expression, crazy thing like this, we could use these properties to greatly simplify what we have on the right-hand side of this equation here. So let's use these properties of logarithms to see how they would help us to profit in this case. Oh, one more fact, actually, before I go forward. And this is maybe a general fact from the chain rule. Let's say that we have let's say that we want to take the derivative, natural log of f of x, where f of x is some complicated expression involving x. Is there a nice way to express this? I mean, ddx of natural log of f of x. So we want to take the derivative of log of f of x. So yeah, this is a composition of functions, right? We're taking the output of f and we're shoving it into this other function log. And what's the derivative is the question. Well, number of ways of thinking about it. Let u equal f of x or whatever, then d, well, whatever. What this is going to be, this is like log of garbage, right? So the derivative is going to be 1 over garbage. That's using the fact that the derivative of natural log of x is 1 over x, multiplied by the derivative of the garbage. So translating that here to this situation, we get the following. And this is like a general fact that you can use for the rest of your life. Whenever you see the natural log of some complicated expression and you're taking the derivative of that, you can just put the derivative upstairs and divide it by the function, the original function, downstairs. So let's apply to this situation these 4 factoids that I've got developed here. And let's start by taking the natural log of both sides of this expression here. So Do I need to conserve space? Maybe. Let's go down here. Down here. So take natural log of both sides. So natural log of y is equal to the natural log of this god-awful mess. I'll write it all out. And now we can simplify this right-hand side using properties of logarithms. First thing to notice is that we have the log of a quotient, so that's the difference of logs. So this is the same thing as natural log of 2x plus 3 cubed times sine to the 6th of x minus the natural log of tangent 2x. Is that comfy? And then we can break up this product. This is a product of this cube bit and this sine bit. We can break that up into a sum of logs. And then finally, we can use this property to take these powers, okay, and move them out front of the log. Now, none of what I'm doing right now is calculus. This is all just it's not calculus. It's just using properties of logarithms. Nothing I've done thus far is calculus, right? But now I'm going to do calculus. So this is natural log of y, is all of this mess here. Now I'm going to ddx both sides. So now ddx both sides. And what do I get on the left? What I get on the left is, by this rule, y prime divided by y. And what do we have on the right? Well, I have to take I'm going to use the sum rule, right? The derivative of this piece is 3 times, now it's f prime over f. F is being played by 2x plus 3 here. F prime, therefore, is 2. F is 2x plus 3. Can you see that? My bad. Next term, we have 6 times the derivative sine of x is cosine of x divided by sine of x. That's f prime over f again, where f is sine of x. And then finally, we have minus tangent 2x. So we have downstairs, we know our f is tangent 2x. And upstairs, what do we have? Well, the derivative of tangent 2x. And I kind of want you to just know what that is. That's going to be 2 times the secant squared of 2x. Why? Because of the chain rule. This is like tangent of garbage. The derivative of tangent of garbage is secant squared of garbage times the derivative of garbage, which is 2. Okay, then we can clean all of this up to some extent, right? So we get y, this is equal to 6 over 2x plus 3. That is, by the way, a synonym for cotangent. And I'm trying to figure out if there's a nicer way of writing this. And I guess there is, because secant squared is 1 over cosine squared. And tangent is sine over cosine. So we could bring the 1 over cosine squared from the numerator down into the denominator, getting cosine squared in the denominator, and then 1 of the cosine. So we get minus 2 over cosine 2x sine 2x. Can you read that? I hope so. You can't read that. I'll write it nicer in the next line because I'm not done yet. This expression here is y prime over y. Yeah, you can think of it, yeah, y prime over y. What is it that we want? We want dy dx. Remember, that's what our target here. So what we can do is multiply both sides of this equation by y. And what's y? Oh, right. What's y? Y is this god-awful mess. Okay? So really what we're just going to do is take all of this and multiply it by that. And that's y prime. Is equal to y times all this. So 2x plus 3 cubed sine of x to the sixth divided by the tangent of twice x times all this mess here. Plus 6 cotangent of x minus 2 over cosine 2x sine 2x. I keep losing that part of it. Yeah, that's the derivative. And believe it or not, this is exactly the same derivative you would have gotten if you had applied all of the rules for derivatives in the right order to this guy here. Okay, so that's logarithmic differentiation. That's what's meant by that. There is an exercise in the worksheet, which you can see. Another exercise that you can try out applied to the fifth root. And again, it's not that this is something that you, like a function that you couldn't take the derivative of. You could. But it's just that with logarithmic differentiation, that's made easier. There is an example of a situation where probably you don't know what to do, or you wouldn't know what to do in order to find the derivative. And that's given by exercise 12.5. Use logarithmic differentiation to compute y prime, where y is equal to x to the x. We haven't really, well, no, that's not totally, well, yeah, there probably is a way, frankly, of doing this one. There's always a way, but it would have required a little bit of additional sort of technique, like maybe, whatever. Try that. Try to do 12.5 and 12.4 using logarithmic differentiation. Okay. I have about 8 minutes left, which is enough time to say something about related rates. Because before we want to talk about related rates, we want to delve a little bit deeper into this notion of relationships between quantities of interests. So there are lots of these in the world, and so before we get into related rates, let's talk about relationships. And this is just any sort of relationship that you can write down between two quantities, not unlike what we were just doing. There, in implicit differentiation, we were talking about relationships that were more complicated than just y equals f of x. Things like x squared plus y squared equals 1, or things like xy squared minus x squared plus 2y equals 2. We can regard this as a sort of relationship between x and y, because if you know the value of, let's say, x, then you could, in principle, figure out what y is, what the values of y that would solve or satisfy this equation would be had you been given some value for x, right? So we want to just sort of think about these things as being like relationship equations, but we want to particularly focus on sort of real world or physical kinds of applications. For example, we've already talked about how, like, if you're riding your bike, you might be interested in the readout of your speedometer or something like that. That would be an example of a relationship between time and speedometer or speed readout. But there's lots of these things that you've learned over the course of your life. For example, a radius, the circumference c of a circle of radius r, we can relate the circumference to the radius with a very simple functional relationship. These are related by the equation c is equal to 2 pi r. Now, I'm not telling you anything you don't know. You learned this in high school. You might not have known or learned why that is. In fact, if you go on to take calculus, I believe calculus 2, you'll learn why that is. Is that true in calculus 2? I think so. You'll learn why this is. You'll get a proof, in other words, why this is the case. But for now, let's just accept this to be true. Similarly, the area, which we might denote A. Why A? Because A is the last letter of the word circumference. That's why. The area A of enclosed by a circle, again, of radius r, is given by the relationship equation A is equal to pi r squared. Again, nothing that you haven't learned previously. You might not know why that's the case, but it is. Okay? Another example, the hypotenuse hypotenuse C, or maybe I should say the length of the hypotenuse. Just chill out, okay? Give me a break. Hypotenuse C of a right triangle is related to, that's how you spell triangle, like that with an L, is related to the other two sides, A and B. Again, the length of the other two sides, whatever, by c squared is equal to a squared plus b squared. And in principle, of course, you could, because this is a length, you could take the square root of both sides and it would be c is equal to the square root of a squared plus b squared. But we could also write the relationship like this. It communicates it equally well, right? We'll develop later the fact that the surface area of a cylinder of height h, and I should call surface area S, because S is the first letter of the word surface, of height h and radius r, I'll draw you a picture, is surface area. So it's twice the top and the bottom, which ends up being 2 pi r squared. So S is equal to 2 times pi r squared, and then the surface of the lateral side, we'll talk about this formula, is 2 so circumference is, snip, 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 fold out, rectangle, height h, 2 pi r h. That was whatever. This formula we can develop. We will in class at some point. Here it is, what I'm talking about. So that's a cylinder. It's like a toilet paper tube. Height h, radius r. And it turns out that the surface area of this thing, and I'm including the top and the bottom. That's what this term right here is coming from. So it's a closed cylinder, I guess. Whatever. Has this surface area. All right. The game with this related rates thing, and I realize I don't have much time, is that we're going to take relationships like this and use the machine of calculus to compute, let's say, the change in circumference of a circle if we're given information about the radius of the circle and how the radius is changing. We are going to find a relationship between the rates of change. We are going to relate the rates of change in R to the rates of change in C, in other words. We're going to learn general techniques for doing that. Similarly, we'll learn, if we know the rate of change of R, we can figure out the rate of change of A, etc. If we know the rates of change of A and B, we can figure out the rate of change of C, etc. Okay, so for all of these different kinds of relationship equations, and there are gobs and gobs and gobs of these, there's no shortage of these, we can use the machine of calculus to relate the rate of change of one quantity with the rate of change of another. Okay, that's what I mean by a relationship equation. And in the next video, we'll get into all of that. Okay, that's enough for now. So long. See you next time.